All right, so welcome to the next session. Our next speaker is Jean-Christophe Filliatre, and he's going to talk about his Why3 approach, and in particular how to prove properties on inductive predicates. Welcome.
Okay. Thank you, Peter. So, hello everyone, I'm Jean-Christophe, and I'm going to tell you about what we did recently in Why3 as part of the master internship of Henri Saudubray, who I supervised with my colleague Andrei Paskiewicz. So for those of you who don't know, Why3 is an intermediate verification language like Boogie or Viper. So it has its own programming language called YML. It has its own logic that we designed for program verification with a VC gen in between. And then there is a lot of plumbing to apply logical transformation on the VCs and send them to existing theorem provers, including SMT solvers. And then outside of our team, there are people developing program verifiers for various languages. So here I'm mentioning, for instance, GNATproof, a tool for Spark Ada, Creusot, a tool for Rust, from Xavier, and Pharmacy for C, and Camlir for OCaml as part of other tools. Okay. So first I'm going to describe what is the logic of Why3, and then I will say a few words about the way we do currently proof by induction in Why3, and then I will move to the topic of this talk about doing proof by induction on other inductive predicates in Why3 with a new addition to Why3, and then I will show an application of this new construct. So the logic of Why3 is the logic of compromise, and it echoes on Benjamin's slides earlier, that it tries to be expressive, which is good for a user, but also at the same time it has to be simple enough for SMT solvers, and also for users, because when you debug while doing program verification, at least in Why3, you typically look at the logical statement of the VC, which is not proved yet, and the simpler the better for the user. So, okay. So what we ended up with is an extension of first-order logic of our own, which was described more than 10 years ago in this paper, and more recently formalized in a very nice Popple paper this year. So if you are curious. Okay, so what do we have? So for instance, we have a type polymorphism and algebraic data types in the logic of Why3. So you can define, for instance, the usual polymorphic list like this, and you can build a list like this constant at the bottom of the slide. You can do pattern matching over algebraic data types. You can define recursive functions and recursive predicates, and they have to terminate. So the logic of Why3 is a total logic. Okay. So for instance, here we are defining in the logic recursive functions to compute the length of a list, okay, using pattern matching and recursive call, as you would do in any ML programming language. And you can state things about such a function. So for instance, you can state that the length of any list is non-negative. So in a moment, we are going to see how we can prove this, but at least we can state it for the moment. Okay. And last, this is the subject of this talk, you can also define inductive predicates the way you would do with the CogProof assistant, for instance. So here I'm introducing two examples of inductive predicates. So the first one, a name step is between two integers. So this is, for instance, one way to describe a non-deterministic relation between two integers. So the first one could be described with simply equality and disjunction, because it is simple enough. But the second one, the name predicate, is slightly more interesting. Okay, this is the transitive closure of the first one. Okay, so it has a step constructor here, saying that if you are in the name step relation, then you are in the name relation, and then you have this transitivity case on the second line. Okay, and again you can state things about such predicates. So for instance, in this case, you could state that whenever you are in the name relation, then you are strictly decreasing while staying non-negative. Okay. Okay. So when it comes to using automated theorem provers and SMT solvers in particular, we have to translate this first-order logic with a lot of extensions of ours into SMT2 logic, for instance. Okay, which means that we have to encode things. We have to encode type polymorphisms, we have to encode algebraic data types and pattern matching and so on, and also inductive predicates. And we are possibly losing completeness in the process. Okay, I will give 2 examples right now. So for instance, when you declare some algebraic data types, like the polymorphic list we already saw, then we are going to translate that to the SMT solver as some uninterpreted type list, a constant nil, a function cons, and injectivity and inversion principles, that like the fact that any list is either nil or cons. But we cannot throw the induction principle that comes with the list to the SMT solver, because this is not something we can describe in first order logic. And similarly, when you define some inductive predicate, like this nim predicate, we are going to turn that into some uninterpreted predicate in the logic with 2 axioms. The 2 cases for the definition are simply thrown as they are as axioms to the SMT solver. And there is also an inversion principle saying that whenever you are in the nim relation, you are either in the step case or the pass case. But again, there is no induction principle that we can express in first order logic that we could send to the SMT solver. Okay? Yeah?
Question. SMT has data types. In the case of list, is there a...
Okay, yeah, that's a good question. Yeah, I should have mentioned that. That's right. But this does not marry quite well with our encoding of type polymorphism. So this is not that easy for us to use the data type facilities that you have in some SMT solvers. But you're right. So in some simple cases, we could do that, yeah. But yeah, thank you for pointing this out. Yeah. And similarly, some of the SMT solvers, they do a little bit of proof by induction. I'm going to say that in a moment. Okay. Okay. So we are not sending induction principles to the SMT solver. So how do we do proofs by induction? Okay. Let's say, for instance, that we want to prove this trivial property about the length function, that the length is non-negative. Okay. So some SMT solvers that do a little bit of proof by induction by themselves by trying to basically, when they find counter models, they try to find the smallest possible counter models for some measures over algebraic data types when we use the data types of SMT solvers. So I should not say this cannot be proved by any SMT solver, but generally speaking, they can't do that. Okay. So what we do is that we do the proof by induction on the Why3 side using a lemma function. Okay, so the lemma function is a program function, a ghost program function, whose purpose is to build a proof. Okay, and if you don't know about lemma function, you go and read this very nice book on Daphne by Roston, which appeared 1 year ago, which is full of lemma functions all over the place. Okay, so it looks like this. Okay, so it's a program function. So here, this let keyword introduces a program function in the YML part of Why3, in the programming language of Why3. But this lemma keyword is also saying that this is a ghost function, and more precisely, a ghost function with, whose purpose is to build a lemma. Okay, the proof of a lemma. Okay, and this function returns nothing. The purpose of this function is to build a proof. Okay, so what we are proving here is a postcondition, but we could have also precondition as well. Okay, and it must terminate because this is ghost code, and ghost code must be terminating. Okay, so here I'm providing explicitly a variant, but Why3 is smart enough to figure out this simple variant by itself if you omit it in that case. Okay, and then you have a program after the equal sign. Yeah, so the last 4 lines is the body of the function. Okay, and here we are doing a pattern matching over the list with match, and then in the 2 cases we have some ghost code. Okay, so in the first case there is nothing. Okay, so we are letting the SMT solvers doing the proof in the nil case, And in the const case, we are simply making a recursive call to the function length non-neg, which is a recursive lemma function. Okay, and that's it. Okay, so we are performing the proof by induction by doing the recursive call by ourselves. Okay, here. So it could be the code could be more complex here. Okay, but here, in this case, we simply have to make the recursive call. And it's a traditional call to a function, so the decision is going to require the precondition of that function, if any, and providing then the post condition and generating a VC for the decreasing of the variant and so on. Okay. Yeah. So that's the first point. So we prove a ghost function like we would prove any other program function. The decision does not care about ghost code at all. Okay, you can forget about what is ghost and not ghost when it comes to compute the VCs. Okay, so we prove the function, and once the function is verified, like any other function, then there are two things. So first, we turn the function contract into an axiom. So now we are done with the proof of length non-neg. So we can throw this axiom and send it to the SMT solvers. Okay, and beside, you can call this ghost function like you would call any other ghost function in your code. So for instance, if you have some list at hand, like my list here, you can call the ghost function over that list. And like with any other function call, you would have to prove the precondition. There is no precondition here, and you will get the post condition, which would be the fact that the length of that list is non-negative. Okay, so if you know that, yes?
Are 2 and 3 sort of different options, or is 2 a step on
very good point. So so the third one is, so we do the second step in any case, okay? And the third case, the third point is up to you. So it's up to you to call the lemma function. So most of the time, the SMT solver are smart enough to apply the axiom automatically, okay? And you don't have to do that. Okay, because on this one the trigger will be very, very good. It will be length of n, and you wouldn't have to call it. But that's a good question, because in Daphne, for instance, the second step is not performed. So by default, something you proved as a lemma function should be called explicitly as part of your code. So it is not sent to SMT solver. So this is a design decision. Yes.
Do we select a trigger in step 2?
No. So there is syntax in Why3 to select triggers, but since we are using so many different theorem provers, we prefer letting the SMT solvers figuring out the triggers by themselves. But I almost always have this question when I'm talking about Why3. So. Okay. Okay, so I'm making a side remark with this slide that this is not the only possibility. Another possibility in that case for the length function would be to define the length functions and proving a property about it at the same time. So we can do it like this. So we can define the length function as a program function with let, but also as a logic function at the same time. So this function keyword is to tell Why3 that the function is also part of the logic, okay? And as part of, and then you can put a post condition to that function, like you would do with any program function, okay? And you have to prove termination because that's a logic function, and the logic function should be terminating. And then you do the definitions, and once you are done with the verification of this function, then you have the logical definition of that function in your context. So the fact that the length of L is equal to that match to the body of the function. But you also have the properties that you proved with these ensures, and maybe others if you have several post conditions. Okay, so that was just a side remark to say that this is an alternative to doing the logical definition first and then the lemma function, at least in simple cases. Okay, so now I'm coming to the point of this talk. So when we have inductive predicates involved in lemmas that we would like to prove, we would like to be able to do the same, which means to to do proofs by inductions with lemma functions inside Y3. And yeah, so that's what we added to Y3 recently. Okay, so there are things in the design space. So we like the idea to stick to the usual practice in Y3, which is to write your proofs by induction as lemma functions. Okay, so that all over the place inside the lemma function you can throw a piece of ghost code to help the SMT solvers with intermediate assertions and stuff like explicit calls to other ghost functions. Okay, and we also like the fact that you're making your own recursive calls with whatever arguments you want, instead of using some automatically generated induction principles that would come with the inductive definition. Okay, that's the first thing. And the second thing is that we were careful in not polluting the logical context with any new type of function or axioms that would come from the inductive definition. Okay, so for instance, it would seem natural to take the inductive predicate definitions and then to macro-generate some algebraic data types, which is the finite shape of the proof, okay, and then to do your traditional recursive lemma functions over that algebraic data type, okay. That we could do, but that would introduce new types and functions and inside the logical context, which is going to be annoying for the SMT solvers, because now they have more terms and more functions to apply, and possibly more ways to instantiate universally quantified axioms. Okay. So what we added to Y3 is two things. So first, a new construct so that we can match over some inductive proofs to do the case analysis inside the lemma functions. But then there is something else, which is we have to prove that the recursive calls are going to be on smaller inductive proofs, okay, to ensure the termination. So we also extended the variant of lemma functions for that purpose. Okay, so it looks like this. So if I'm using this example again, I want to prove that whenever I have nim of x and z, then z is smaller than x. Okay, I can do this proof using a lemma function, okay, with this letrec lemma, and I can do the case analysis over the inductive proofs with this new match inductive construct. So you have to name the hypothesis. So there was already a notation in Y3 to name pre or post condition, so that was convenient. Okay, and then you can, after the match inductive, you can put the name of one of these hypotheses from your context, okay, which lives in some inductive data type, like here. And then the body of the lemma function is just here a case analysis, and similarly to what we did with the length non-neg, in the first case, this is simple enough for the SMT solver to conclude, so there is nothing in the ghost in the lemma function. And here in the recursive case, we are making two recursive calls to the lemma function. Okay, yeah. Okay, on x, y, and yz. Okay, so it works like this. Yeah.
Does the match inductive thing only work specifically for requires clauses that are of one inductive type? What happens if you have a conjunction or any other?
Okay, I think I'm going to answer that question in a moment. Okay, so yeah, you cannot use it everywhere, so it has to be in ghost code for sure, but not at any places. Yeah.
Do you have syntax for naming the post condition of the ghost calls that you make?
The post condition of here you mean?
Provide you some fact. If you want to match on that fact, you will need to name that fact.
Ah, good question. I don't think we have such an example so far.
Maybe
yeah, we should be able to do that. Okay, but I should check. So okay, so yeah. So here, for instance, okay, your question is not about this hypothesis, right?
No, it's about the one produced.
About something that would be the output of the code. Okay, good. So yeah, I should check. Yeah. Okay, so what we did is to actually to disregard this into something we already knew to do. Like, so we are turning the match inductive into several local ghost functions inside that lemma function. So here we have one ghost function called step for the first case of the match inductive, and a second ghost function pass for the second case. Okay, and then these functions, they have several pre and post conditions. So the preconditions are the hypothesis of these various cases from the definition of the NIM predicate, but also preconditions saying that the parameters of these cases should unify the parameters of the hypothesis we are doing the case analysis on, which was the NIM, the H hypothesis in our case. Okay, so these are the unification lines here. Okay, and then the post condition of the lemma function is given as a post condition for these two functions. Okay.
You would motivate the disregarding. Why don't you support the previous construct as built in?
Because then you don't have to change the VCJ and stuff like that. So it was much simpler to go for something that already exists. Okay. Yeah, but you're right. We could have instead patched the VCJ of Y3 to accommodate this new construct. But there was no point in doing that. So
another way to ask my question is: disregarding linear in the size of?
Yes. Yes.
So you don't introduce
Yes.
Are you also supporting nested patterns?
Yes. Yeah. I'm going to answer that question in a minute. Okay. And then the user code that was in the match inductive is just copied as the body of these two ghost functions. Okay. And finally, at the very end, there is nothing else to prove. Okay, because if each of these functions is concluding with the expected post condition, then we know that we are doing the case analysis of some proof inside the inductive predicate. Okay, so we can trivially conclude that then the post condition would hold for any case. Okay. Okay. Yeah.
I didn't see the exhaustiveness track.
Sorry.
I would expect to see an exhaustiveness track also.
Yeah, so first on this part we are doing an exhaustivity check during type checking. Yeah, I should have mentioned that. Yeah, okay. Otherwise, Y3 is going to complain that you are missing some cases. You're right. Okay, and yeah. So there is something to answer the question I had earlier. That since we are going to take the post condition of the lemma function and put that post condition to all these individual ghost functions, then the match inductive should appear in a tail position. Okay. So and the type checking of Y3 is also checking that. So for instance, if you try to use this match inductive somewhere else with something after that, for instance, then Y3 is going to complain that the match inductive is not in a tail position. Okay. Okay, and of course we should be able to prove termination. Okay, because this is ghost code, and ghost code must be terminating. So we also extended Y3 with a new kind of variant with this inductive keyword. Okay, and the meaning is that whenever we will make a recursive call, we will have to prove that we are matching one of the smaller instances of that predicate that we have collected so far. And so there are many ways to collect this hypothesis, okay? And possibly we could collect them transitively if we are doing a match inductive inside a match inductive in a nested way, okay? Yeah. So here is an example. So in our case, I'm inserting this variant inductive H to the previous lemma function. Okay, and so this is provided by the user. In that case, it is simple enough so that it could be inferred by Y3, but we are not doing that for the moment. Okay, so Y3 is going to collect all the smaller instances of the predicate we are doing the analysis on. So in that case, these are the two hypotheses coming from the past case of the NIM predicate, okay, which are unnamed here because we are not making use of them in the ghost code. And then when we make the recursive call, we generate a predicate for the decreasing of the variant. And this predicate is a disjunction which expresses that we should match one of the smaller instances that were collected so far. So in that case, we have collected two smaller instances. Okay. So when we come to the recursive call, we generate this verification condition saying that we are indeed in one of these two cases, and that's here trivially true by the left part of the disjunction. And similarly, when we make the second recursive call, we have this disjunction saying that we are in one of these two cases, and in that case, the right part of the disjunction is trivially discharged. Okay, and you can mix. The nice thing is that you can mix this new kind of variance with other variants in a lexicographic way. Okay, so for instance, you could have a variant which is a lexicographic tuple of an integer, an inductive proofs, and a tree, for instance, or whatever. Okay, and for the VCGen of Y3, it makes no difference. Okay, so it will generate the predicate corresponding to the lexicographic order, and when it comes to the inductive, it will generate this disjunction of equalities that we saw on the previous slide. Okay, and we also accommodate mutually inductive definitions, and then if you have a mutually recursive lemma functions for proving things about your mutually recursive inductive predicates, then you can have variants for the various recursive lemma functions that could be different, like you would do for proving the termination of mutually recursive functions as usual. Okay. Okay. Yeah. Basically, that's it for these small additions to Y3. But now I'm going to
Do you also support nested inductive definitions, like a tree where you have a list of nodes?
Not yet. But I understand the question. I'm familiar with that from the proof assistant context. But yeah, not yet. I'm going to say that a few things about that at the very end. Yeah. Okay. So in the very last slide, I'm going to try to convince you that this could be useful in something like Y3. So I took a proof that Gerard did a long time ago with Koch. Okay, about so before doing that, in the 80s, Gerard gave a lambda calculus course at various places in summer schools and universities and stuff like that, where all the lambda calculus notions were programmed in the OCaml programming language. Okay, so you define the lambda terms with De Bruijn indices, and you program a lot of things over, like reduction and parsing, printing, and you implement various computation strategies, and then you do the church numerals, and then there is even a quick sort in a pure lambda calculus implemented in these lecture notes, where basically you encode a small list of church numerals in the pure lambda terms, and then you sort them with a huge quick sort lambda term. Okay, and but apart from that, this is a standard lambda calculus course. Okay, with the results up to the Prism theorem and Levy's cube and stuff like that. Okay, so it's roughly 3,000 lines of OCaml code. And a few years later, Gerard did the same using the Koch proof assistant. Okay, and there is slightly less material in the Koch proof compared to the OCaml implementation, but it goes up to the Prism theorem and its corollaries like Church-Rosser and property and Levy's cube. Okay, so now it's defined and verified inside the Koch proof assistant. Okay. So inside this proof, which is a moderately sized proof. There is plenty of inductive predicates, okay, for reductions and parallel reductions and set of radixes and stuff like that, okay, and almost 80 proofs by induction, not surprising, okay, and 2 algebraic data types for lambda terms and lambda terms with marked radixes, okay. So it was a good candidate for us as to see whether we could translate this to Why3 and hopefully with a slightly smaller proof in Why3 thanks to SMT solvers. Okay, so for instance, this is one of the very first proofs in Gerard Coq files, saying that if you can make a reduction between M and M prime with 0, 1, or several beta reductions, then you can make that reduction under a lambda. Okay, yeah, and the proof is by induction over the hypothesis that there is a reduction, and this red predicate is defined as an inductive predicate. Okay, so you are making the induction over that hypothesis, and you are rebuilding the proof that you can reduce under the lambda in some very simple and isomorphic way. Okay, and so the same proof in Why3 would look like this. So it's no longer. It has basically the same structure, but it's kind of different from Coq, where the induction tactic of Coq is applying some induction principles that was automatically generated from the definition. Here we are doing something slightly differently. We are defining a recursive lemma function, okay, to do the proof, but with the same statement, same hypothesis here and conclusion here, and we are performing the proof by case analysis over the 3 cases of the inductive definition. So it looks much different. This is not that different because in Coq, if you, at the very end, if you take the proof term, if you inline the induction principles, and if you beta reduce what the proof term, then basically you will get a recursive function, which is exactly this one. Okay, so this, yeah.
The case that if you write a program lemma in Coq, you can write almost this.
Yeah, yeah. I think if you are Christine Paulin, you can do that directly in Coq, but normal people, they use the induction tactic instead. Yeah.
What is the reason why the reflexive transitive closure has been defined using 3 cases? I would always define it using 2 cases.
Yeah.
Take 0 steps or 1 followed by many, and then just prove that's transitive.
Good question, but you should ask Gerard. So I don't know. So we made a faithful translation from the Coq proof to. But you're right. There are plenty of ways of defining the reflexive transitive closure, and this is one, and maybe not the most natural one. Yeah, natural one. Yeah, yeah. Good point. That's a good point. Okay. Yeah. Yeah. And so Henri was did a very good work at translating all of Gerard proofs to Why3 during his internship. And basically, at the end, we have something which is 2 times smaller than the Coq proof. Okay, at least if you count the total size. Yes.
This was a Coq proof from the 90s. Right?
Yes.
I mean, I think the sort of lemmas you showed today, you would do induction auto, and it would be a one-liner. Most of these things. No?
Maybe, yeah. So yeah, that's a pity. Yeah, but that's a good point because I think that this proof does not even type check with recent version of Coq. So someone should port it to a recent version of Coq and try to make it smaller. That would be yeah. So maybe the comparison is not fair.
Would be more faithful.
Okay, so thank you for that remark. Okay. And basically, we have the same number of inductions in, not surprisingly, in Why3. Slightly smaller because there were a few cases where the SMT solver were smart enough, I guess, to do the proof automatically because the induction was not really needed, or yeah, I guess that was the idea. Okay, and yeah, so it was a kind of a good surprise for us, because that's typically not the comfort zone of Why3 to do such kind of proofs. Okay, but that was a pretty cool experiment. And there are a few differences between the 2 proofs. So for instance, we have nothing like natural integers in Why3. So there are a few places where we we had to add preconditions because our de Bruijn indices are integers. Yeah.
To make, again, a more faithful comparison, could you just use your inductives to define a NAT type, and then you would have to redo the same kind of work that Coq has to do?
Yeah, okay, so yeah, I could define, for sure, I could define an algebraic data type NAT in Why3, but then I will lose the arithmetic abilities of the SMT solvers, which I don't want to do. So,
But then it would be a more sort of head-to-head comparison, and then you could compare the two versions.
Right. Okay, so we are, okay, yeah, that's right.
Yeah, but you don't want to do that.
Yeah, no, I don't.
That's the point of using Why3, you don't want to do that by hand.
Well, but if you had an explicit diff, then you could show more explicitly, this is what we get, right? Rather than comparing apples and oranges.
No, what you get is you can still use SMT.
Yes?
Why don't you have an induction scheme based on the natural numbers? That's what I thought you said.
I cannot express that induction scheme in the first order logic of SMT solver. So.
Oh, for the
Yeah.
SMT, I see.
Yeah.
Thanks.
Yeah.
Could you support custom-defined recursion principles, for example, for natural numbers?
Yes, as long as you are writing the lemma function, the recursive lemma function by hand, you can do any kind of recursion pattern. So you'll have to prove that that it is terminating, but then it's up to you to make the recursive calls you wish. So it could coincide with some custom induction principles, yeah, for sure. That's one nice thing about doing proofs by induction with lemma functions instead of using generated induction principles that are not always the one you want.
I don't know Why3 well enough, but if you have indexed inductive data types, you could maybe construct a data type that allows you to do match inductive to do recursion on the natural.
Yeah, so this is something we don't have for the moment. That's the very last line of my recap, but I think it relates to your question. But I see no reasons why we could not do that. So, okay. Yeah, so this is a small addition to Why3 that I just presented, and for the moment it is kind of it has some limitations related to some of your questions already. And in particular, we intend to add the support for infinite trees. Okay, when you have infinite branches in the definition of your inductive predicates. So it looks like we could extend what we have done so far to accommodate this as well, but this is not yet implemented.
Another possible encoding is for every predicate that is defined, to generate another version of the predicate with one extra argument, that is a NAT, that's counting the depths of the tree. And then you can do all your induction on the depths. So I'm not suggesting that would be very practical, but
that's what we investigated in the first place. Okay, but this was introducing new types, new predicates, and we disliked this for that reason. But we started exactly like this, by trying to micro-generate from the definition other objects on which we could do more traditional recursion proofs.
This encoding will support infinite branches out of the box.
Yes, that's right, but yeah.
Okay, thank you. So we do have more time for questions.
I think there was one more question.
Yeah, no, we have more time.
So whenever I'm doing proofs, they're normally wrong until the end. So what's it like for them to be failing with this match inductive? What's the key?
Oh, yeah. So you mean when the VC is not proved, right? So okay. So we have several tools in our case. So like I would say like in any program verifier. So typically you can have a look at the VC statement which is not proved. Okay. I find personally that this is one of the most efficient way of debugging proofs. Okay. And then you have counterexamples from the SMT solver. okay, that you can ask for some of them. And we have this in Why3 as well. And then, as usual, you can insert intermediate assertions. You can try to throw an intermediate lemma, and you can try to prove a more elementary property. Yeah, there are many ways of doing that. So there is no general answer to that question, but.
Why3 also has a tactic language. So you can, as Jean-Christophe said, you can see the proof task, but you can also attempt to prove it manually, even if you wanted to investigate why things aren't proved.
Yeah, but it's much more limited than the tactic language of proof assistant, for instance. So, but you can write.
Yeah, Robert?
So earlier I asked you about nested induction, for example, with lists. So you said you don't support that, but do you see any challenges in this?
No, that.
Because so in Cork I always find this to be still a bit iffy, because in Cork I don't get the induction principles automatically whenever I do nested induction. And second of all, whenever I write down functions on nested inductive data types, I need to be extraordinarily careful that I get the structural recursion right. And I guess that since you are doing using variants anyway for termination, there is an opportunity here to do this better than Cork.
Yeah. Okay. So I think that we should think about it, but this is related to these smaller instances that we are collecting, that Why3 is collecting to ensure the termination. So we should be careful in collecting them in nested definitions as well. So.
Yeah, but I could imagine that if you have a nested inductive definition, that you also write some kind of a nested rec lemma. So that in your mesh there's somewhere, let's say, like a nested use of a rec lemma.
Okay, that you can do. You can even have a recursive lemma inside a lemma, for instance, or it could be mutually recursive if you wish. That's fine. So,
okay.
Yeah, so that's. But for termination, I was more concerned about termination and collecting all the smaller instances so that you can make the recursive call, and Why3 is happy with the termination. So that would be maybe the difficult part.
Finally, one last thing that would be interested is to allow nested induction via data types that are natively supported by the SNP. For example, that you can make a tree where you have like an array of trees, and then if you want to do proofs about this, you can make use of the array theory of SNPs.
Okay. Yes, but so again, we have trouble using the built-in data types of SMT solvers because of our encoding of type polymorphisms.
Right. Okay, that's what.
But that I mentioned earlier. But yeah, I agree. That would be nice. Yeah.
Because sometimes I just don't have polymorphic types. Let's say I define expressions for my language that is entirely monomorphic, but then I still might want to have a list or an array of expressions somewhere in there. And then if I can get the SNP to just kill things there, automatically that would be fantastic.
Yeah, that's right.
So I have a question about the language design. So you decided to put this feature into Why3, but it's internally handled by a translation into a more basic Why3. Right? So you could have taken the perspective that whoever wants that feature, whatever Clouseau or Pharmacy, should put that into the front end. So how do you take such decisions? When do you decide to grow the Why3 language, and when do you say, well, this is something that the front end should take care of?
That's a good question. So we are also using YML directly to do program proofs. So that's what I like doing on a daily basis. So this is my program verifier of choice. So I like adding new stuff in YML, and then if this can benefit to others on top of it, good for them. But and then I could also say that now, if any of these tools on the left would like to add a match inductive, it could be translated to the match inductive of YML PDD. So.
Okay, well, thanks again.